Well, good afternoon or good morning, depending upon where you are, folks. John Barba here from Takeo Comfort Solutions, and welcome back to the first springtime Takeo Tuesday. We're really excited to have you with us on this. Well, I don't know about where it is, what it is like where you are, but here in New Hampshire, it's kind of rainy and overcast. But hey, it's spring. There's no snow on the ground, so we're raring to go. Welcome, everybody. Thank you so much for joining us for today's session. And today's session is going to be on flow, head, system curves, and pump curves. And as the slide says, it's a residential focus today. So we'll be talking mostly about that kind of stuff and your typical residential hydronics application and how it impacts circulator selection. We're going to talk about CV and pressure drop through mixing valves and things like that. So hopefully that you'll get a lot out of this, and it can help you make some good choices on your next job. Couple things, just some housekeeping notes real quick. First things first, if you look on your control panel, you'll see a couple of things. Two most important. One is the handout section. I have three handouts for you today. Just some things that'll help you out. You don't need to have them for the class, but download them at your convenience so you'll have them for future reference. And then also there's the chat question section. That's the most important. That's how you're going to ask questions. So if you could all do me a favor, just type in a little hi, hello, how are you kind of thing there. So I know that you can hear me. I know that you can see me, but I want to make sure that you can hear me. Okay, great. We've got a bunch of hellos. Excellent. Terrific, terrific, terrific. Appreciate it. So throughout the program, please type in your questions as they occur to you. I don't particularly like holding all questions to the end because that basically says I don't want to hear from you till I'm done talking, and I don't particularly like teaching that way. So please ask your questions as they occur to you. I will stop every few slides and review what's new and upcoming on the what's new in the question section and try to answer them as best I can. I don't know all the answers. I don't know anybody who does have all the answers when it comes to hydronics. So, but I'll try and share with you the best information that I have, and any questions that we can't answer, we'll find out the answer and get back to you. So with that, super psyched to have you guys with us today. And as always, we love ourselves some Takeo Tuesdays. So let's get started on flow, head, system curves, and pump curves, because we got again, there's a lot of material to cover. So let's get right to it. First, let's just discuss the flow and head, because these are the two things that make a system work, okay? Your circulator selection is important. The amount of flow that goes through a system, how it goes through the system, is going to determine not only the relative comfort of the system, but also the relative efficiency of the system. I've been a long time proponent of the notion that overpumping is kind of a critical problem that we have in the residential hydronics industry. And the reason it's a critical problem because it overpumping will limit the overall efficiency of the system, but it's also a problem that has no noticeable symptom, meaning the system's going to work. You overpump, you're still going to deliver BTUs. Nobody's going to freeze to death and call you up and blame you, okay? And usually that's the number one hurdle that we're worried about in a residential hydronic system. The symptoms generally show themselves later on in terms of problems. First off, the number one system is the system's never quite as efficient as it could be or should be. It might not be the efficiency that the customer was paying for, thought that they were getting. That's the short term. The long term is when we overpump, we promote short cycling of the system. And when the system short cycles, we start to wear out very expensive and complicated moving parts in a system, especially in the boiler. Could be a blower motor or an ignition module on a ModCon boiler, that sort of thing, that generally costs a lot of money to replace. So those are the longer term symptoms of overpumping. So what we want to do with you today is kind of show you how to come up with the approximately close flow and head and how that works with circulator, with pump performance curves. So flow and head, you can't really separate them. They go together. Flow is like the pulse of the system, and head is it has to do with the restriction. All right, so you can't really separate them. As flow goes up, head loss goes up exponentially. All right, it goes up by a function of the square of the increased. And we're going to show you how to figure that out. We're going to show you how to figure out flow, and then we're going to show you how to figure out the head loss and show you what happens to head loss when flow goes up. So flow goes up, head loss will go up exponentially. Write this formula down, folks. This is the universal hydronics formula. This is how we determine flow rate. All right, in a hydronic system, a closed loop hydronic system. And the universal hydronics formula states that GPM is equal to BTUH divided by, and I'm going to put some parentheses here for you just so you understand. GPM equals BTUH divided by the product of delta T times 500. All right, identify the terms. GPM, that's the gallons per minute flow rate you need to deliver the BTUs required. BTUH, of course, is the BTUs required. That's your heat load. Typically, we'll use the BTU load under design conditions so we can size the circulator for the worst case scenario. So GPM, gallons per minute, BTUH, that's the load at any given point in time, but it's the load we're designing for. Delta T is the designed for temperature drop of the fluid as it goes through the system. Okay, we design around a delta T because we have to put a benchmark down here. Typically, with North American residential hydronics, we'll design to a delta T of 20. That means the water will go out at 180 degrees, come back at 160 degrees if we're talking about a cast iron high temperature system. Low temperature boiler, the water might go out at 120, come back at 100. All right, that would give you an average water temperature of 110. In the previous example, with the water going out at 180, coming back at 160, that gives you an average water temperature of 170. Right? Delta T, the delta T can be may vary based on the application. Most residential North American hydronics, we will design to a 20-degree delta T. That's traditional, simply because it works and it does make the math easy. You might find residential radiant floor heating might often be designed to a delta T of 10. All right, so it's more of a snug delta T. Why would we do that? Well, we do that for comfort and consistency of floor surface temperatures. An indirect, the heating circuit on an indirect water heater, that might typically be designed around a 30-degree delta T. If we're looking at sizing a circulator for, let's say, the boiler pump for a ModCon boiler, the manufacturers will give you the choice of designing from anywhere from a 20 to up to a 40-degree delta T. The wider the delta T, the smaller the circulator will need to be. So for our purposes today, we're going to use a 20-degree delta T. Now, the 500 is a mathematical constant, and it represents 100% water. We use 500 when we have 100% water. How do we get that 500? Where does it come from? Well, it comes from multiplying the weight of 1 gallon of water. 1 gallon of water weighs 8.33 pounds, times the number of minutes in an hour. Traditionally, that's 60. There are some places where time stands still, but that's not what we're talking about. So 8.33 times 60 times the specific gravity of the fluid. 100% water has a specific gravity of 1. Times the specific heat characteristic of the fluid. 100% water has a specific heat characteristic of 1, because after all, it takes 1 BTU to raise 1 pound of water, 1 degree Fahrenheit, 1 hour. That's a lot of ones, man. So we put them all together. If we multiply that out, 8.33 times 60 times 1 times 1, we get 499.8. We'll call it 500. Now, glycol is going to complicate things a little bit. Glycol weighs different, it has a different specific gravity, and it has a different specific heat. The only thing that stays constant is the 60. The thing about glycol is every manufacturer is a little different, man. They've got their own different formulas and own different mixtures and things like that. So the number we know is going to go down by how much is going to depend upon what you use. A good rule or good general, get you in the ballpark kind of number, and I'm not a fan of those, but this will help you understand the impact. Let's say you have a 30% glycol, 70% water solution, which is really plenty for any residential application. I mean, that might even be overkill. That might drop that number, that 500 number, down to maybe 470 or 475, right? If you go with a 50-50 glycol solution, like you might have with a snowmelt system, that could drop the number as low as 435. And as this number drops, okay, well, then your delta T times whatever that number is going to be lower. You're dividing your BTUH by a smaller number. Your flow rate is going to go up. The more glycol you put in, you will require a slightly higher flow rate. So again, it's going to depend on what you're using. It's going to depend on what you're using. So any questions out there, type them on in. Let me know how the pace is and how all that is. If going too fast, too slow, can you hear me okay? Let me know. I got to check in every once in a while because every so often the internet goes out here and I don't know if I'm just talking to myself. So if you could just chime in for me, just let me know that that we're still here and that the pace is good. So that's all good. Okay, excellent. So I'm hearing from you. Good, good, good. So let's do one. Okay, let's say I'm going to size a circulator for a big old zone of fin tube baseboard. Let's call it a big old zone of fin tube baseboard, 3/4 inch copper. One of the handouts that I gave you is a pipe sizing guideline based on flow rates. All right, so there's a little interpretation. You have type M copper, type L copper, and SDR9 PEX. So just for your own future reference. So let's say I've got a 30,000 BTU zone of fin tube baseboard, and that's a big honking zone, I'll tell you what. And we want to find out the flow rate, and I'm designing to a delta T of 20. So I just fill in what I know. I know the BTUH, and I know the delta T. I already know the 500. So GPM in this case is going to equal 30,000 divided by 20 times 500. Now again, in math, you always do what's in the parentheses first. 20 times 500 is 10,000. All right, so I'm going to be basically dividing 30,000 by 10,000. This is why we use 500, folks. It makes the math easy. 30,000 divided by 10,000. My required flow rate for that zone is 3. I need 3 gallons per minute. So my circulator is going to have to deliver 3 gallons per minute under design conditions in order to deliver the 30,000 BTUs. So I'm halfway home. I've got my flow rate. Flow rate's the easy part. You know your load, divide it by 10,000 if it's 100% water, and you're good. All right, and if it's standard residential hydronics. So 3 gallons per minute, 3 gallons per minute. Now we have to figure out the head loss or the friction loss. This is the tricky part. So what is head loss? It's friction loss, right? Okay, the water's going through the pipe. It's rubbing up against the sides of the pipe. That's friction loss, okay? So we have to overcome that friction loss / pressure loss, if you will. We hit a fitting, okay? We hit a fitting and we have a change of direction. There's more friction loss or pressure loss there. So we want to make sure we can overcome that friction loss or overcome that pressure loss in order to maintain that 3 gallons per minute flow rate. So that's going to depend on a couple of things. It's going to depend upon the size of the pipe, the length of the run, and the number of fittings in the run, okay? Number of fittings in the run. Because we express head loss in feet of head, there's one thing it doesn't include. It doesn't include the height. All right, if I'm going up to the second floor, do I need to factor in the lift when sizing the circulator? The answer is no, you don't, because it's a closed loop system and what goes up comes back down the other side. Okay, so I don't have to lift the weight of the water up to the third floor. It's already filled and pressurized anyway, so I don't have to lift the water up there to get it there. But I also don't have to worry about lifting the weight of the water because coming back down the other side is the same amount of water that's acting like a counterbalance. Think of it in terms of a Ferris wheel. If I'm sitting on a Ferris wheel, does the motor on the Ferris wheel have to lift me up? No, because there's some other dumb fat guy on the other side going back down. Okay, so I don't need to take into account the lift. Only the friction loss of the pipe, okay, and the fittings, etc. Alrighty, so again, that piping creates the friction. The circulator has to overcome that. Maybe the best analogy I can come up with for you is this guy. If you're a kid who grew up in the late 60s, early 70s, you probably loved you some Hot Wheels. I certainly love me some Hot Wheels. And you used to have to put them, it used to be gravity. You'd use that little purple C-clamp and clamp it to your mother's dining room table, and she'd yell at you for it, but you'd have that orange track going downhill and you could do drag races. Well, I guess enough people's mothers yelled at them that Mattel decided to come up with what they called the Supercharger. And what the Supercharger was this little hut that had these 2 rubber wheels in it that were battery operated. And you could make a big old oval. You shove the car into one end, all right? It hit those 2 rubber wheels. The rubber wheels, boom, shot it out the other side, and it went around the track. As it went around the track, friction caused it to slow down until it came all the way back to the speed shack or the supercharger, and boom, it got shot out again. That's a really good analogy for what happens in a residential hydronic system. The water doesn't necessarily slow down, it's pressure loss, but it's running across orange track, there's friction, it's slow, the water will lose pressure, the car will slow down until it hits the shack again, and boom, it shoots itself back out. If you have too much track, all right, or you don't have you have an undersized supercharger, all right, car's not going to make it all the way around. Good analogy for what might happen in a residential hydronic heating system. So again, the Hot Wheels are like the water, the orange track is your pipe, and the supercharger is the circulator. Let me know if that, I love that analogy. Let me know if it makes sense to you. All right, it's just one of those things that I just love that analogy because I loved Hot Wheels as a kid. Let me know if it makes sense, if it makes sense to you. All right, Lauren says my 6-year-old son has the new Hot Wheels supercharger and loves it. There you go. Excellent. Very cool. Very cool. All righty, let's take a look. Let's take a look at what we have next here. So let's figure out pressure loss. This chart comes from the Copper Development Association's Copper Tube Handbook. And one of the handouts I have for you is just a blank document. It's a document, and the only thing on there is a link you can click to download or to go to the PDF of the full Copper Tube Handbook. It's about 200 and some odd pages of mind-numbingly boring statistics about copper. Table 6 is the important one. It's a pressure loss chart, pressure loss of water due to friction in types K, L, and M copper, and it gives it to you in PSI per linear foot of tube. And you can see we've got K, L, and M copper at different pipe sizes, and over here on the left at different flow rates, because head loss or pressure loss and flow go hand in hand. So let's take a look. Our flow rate is 3 gallons per minute. According to our pipe sizing chart, we're going to use 3/4 inch M copper. So we're going to use 3/4 inch M copper right here. So what I want to do is I want to find my flow rate over here at 3 gallons a minute, follow the line over to 3/4 inch M, and I come up with my PSI per foot of pipe. So it's 0.009 PSI worth of pressure loss for each foot of pipe, all right? So 0.009 PSI for each foot of pipe. Now I have to figure out how many feet of pipe I have, okay? And I can do that by measuring, I can do that by estimating. One way of doing this, especially if it's a retrofit, you can't get in there and with X-ray vision and figure out exactly how many feet of pipe and how many fittings. Best way to do this is to estimate. And I'm not going to say guesstimate because guessing doesn't have a place in hydronics, but estimating does. And it could be as simple as this. It's all right, I'm at the boiler. I got to go 5 feet. I'm going 10 feet up, 10 feet over. That's 20 feet. 30 feet down. That's 50 feet. 20 feet over. That's 70 feet. I'm coming back another 40 feet. That's 110. I'm coming back over 20. That's 130. And I'm coming down 10. That's 140. Close enough, okay? Close enough. If your number has anything other than a 0 or a 5 at the end, you've overthought it, okay? We want to get reasonably close, but that's just the run. We also have to take into account the number of fittings. And again, you can't get up there and count them in a retrofit. So generally, a good method is to simply multiply your run by 1.5. You're adding 50% of that length to allow for fittings and valves and things that are in the way. So you're adding 50%. Look at it like this. A 3/4 inch copper elbow has the same pressure loss as 2.5 feet of straight copper pipe. All right. A 45 has the same pressure drop as 1 foot of pipe. A T will have the same pressure drop as 5 foot of pipe. You can't count them. We have to allow for them. So measured length times 1.5 will give you what we call the total developed length. So for our example here, our total developed length is 285 feet. So I'm going to multiply 0.009 PSI per foot of pipe times 285 feet of pipe. That gives me a pressure loss of 2.57 PSI. Now, circulators, the pressure the head pressure differential a circulator can create is measured in feet of head. It's measured in feet of head. How do we convert PSI to feet of head? Anybody out there know? If you know, type it on in. All right. If you know, type it on in. How do you convert PSI into feet of head? All right. So yeah, multiply it by 2.31. Neil, Jake, Dan, you got that. Multiply it by 2.31. That's 2.31 feet of head, okay, per PSI of pressure drop. All right, so 1 PSI of pressure drop equals 2.31 feet of head pressure loss. So we multiply 2.57 times 2.31, and that'll give us 5.9 feet of head, or feet of head loss in that circulator. So, hey, we're going to call it 6. We're going to call it 6 feet of head. So I'm going to need a circulator that can deliver 3 gallons per minute while overcoming 6 feet of head. Bill O'Donnell asked a question, there are velocity limits in copper piping in heating? Please discuss. Absolutely. That chart that is included in your handouts has velocity guidelines. Typically speaking, we're looking at a velocity maximum of 4 feet per second in our piping. We want a minimum of 2. We want to stay under 4 feet per second. If we exceed 4 feet per second, if we have water going through that pipe like it's like crazy. I mean, I can get 9 gallons a minute through 3/4 inch pipe, no problem. Give me a pump big enough, I can do it. But what will happen if I do that? What would happen to the pipe? What would happen to the pipe and the system if I was running 9 gallons a minute through 3/4 inch copper in a closed loop system? What do you think would happen? What do you think would happen? Yeah, Lauren's got it. Noise and erosion. A velocity noise is the first thing that's going to happen. It'll sound like at the beginning, it'll sound like a to the point where if you really, really overcook it, it can sound like a freaking freight train going through the house. It can be crazy. Hopefully somebody will complain about the noise before the other half of the equation happens, is the fact that you'll erode the pipe from the inside out. Now, we see that as a problem more in like domestic hot water recirculation systems. High velocity combined with high temperature, high chlorine content, running continuously, that'll make a mess of a domestic hot water recirculation system in no time. It takes a little bit longer in a hydronic heating system, okay, because it doesn't run all the time, but it certainly can happen. And usually somebody complains about the noise before the erosion does happen, but the erosion is real and it can happen. Absolutely, absolutely. All righty. Charles says, don't forget the pressure loss of connected things, valves, coils, etc., in your head loss calcs. Absolutely, that cannot be forgotten, and we're going to bring that up a little bit later, Charles. Right now, we're just doing a 3/4 inch zone of fin tube baseboard that's zoned by circulator. But we're going to get into CV and things in just a little bit. Very good, very good. Excellent. Hope you guys are having fun. I know I am. So let's continue. All righty. Pump curves. Now that we know we need 3 gallons a minute at 6 feet ahead, let's talk about pump curves, pump performance curves. And these are the things we at TACO, we figure these things out in the factory based on on how the circulator is designed, the horsepower of the motor, yada, 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 all that good stuff. But fundamentally, what you're looking at are circulators in the residential realm, In the residential realm, we have steep curve and flat curve circulators. In the pump manufacturing world, steep curve circulators a steep curve is known as a European style curve, while a flat curve is known as an American style curve. And there's a reason for that. It just simply has to do with the type of systems those particular circulators were designed for. All right. There's a reason you might have a flat curve circulator, and a flat curve circulator will be defined as, relatively speaking, high flow, but while at the same time being, relatively speaking, low head. All right. A steeper curve circulator like this one here is going to be, relatively speaking, lower flow compared to a flat curve pump, but higher head pressure differential compared to a flat curve pump. Why on earth would you make 2 different circulators, and which one's better? Well, it's the curves are designed for the type of systems that have traditionally been most common in both markets, American style systems and European style systems. Let's explain that for a minute. All right. Over in Europe, this is your typical traditional residential hydronic heating system. Okay, you have panel radiators that are supplied with a home run, like you see here, off of a central manifold. It's a dedicated supply and return to each panel radiator, usually one radiator for each room. And the radiator is controlled by a modulating thermostatic radiator valve. Not a lot, unless it's a radiant floor heating system, not a lot of thermostats over there in typical residential applications. It's a home run direct supply and return, usually in small diameter PEX to individual radiators controlled by a thermostatic radiator valve. Because there are no thermostats in those types of systems, the circulator typically runs 24/7. It starts running in September and it stops running in April. It'll run 24/7. And the TRV will modulate, it'll be opening or closing to regulate the amount of heat delivered into a room and the comfort level in a room. If you were to do the math, I remember we talked about delta T. Typical European heating systems like this are designed around a delta T of about 40 degrees, 38 to 40 degrees. A wider delta T, you've got a big old panel radiator, so it can work with that wider delta T with no problems. But that results in, relatively speaking, low flow rates. If you're trying to deliver 50,000 BTUs at a 20-degree delta T, okay, that's 5 gallons a minute. If you're trying to do it with a 40-degree delta T, that's 2.5 gallons a minute. Lower flow. We're still running very small diameter pipe. It could be 14 millimeter PEX in European examples. That's still going to have a relatively high head loss. So the worst case head loss radiator might have a, relatively speaking, high loss. So for that reason, we have low flow, high head, steep curve circulators for your traditional European style systems. That's why a European circulator will traditionally be a lower flow, higher head, steeper curve pump. Okay, now here in the US, we've got everything. Okay, right now we've got everything. But going back to when we started designing circulators back in the 40s, 50s, and 60s, we have a little bit of everything now, but back then it was usually a cast iron radiator system with maybe with a Venturi tees or a 2-pipe system or a series loop of fin tube baseboards. And these systems were installed in houses while the houses were being built. So we had big pipe. Okay, we had big pipe designed to a 20-degree delta T, big pipe, big loads. We're going to have higher flow rates. All right, we're going to have higher flow rates, but because we're using larger pipe, that head loss is going to be lower. All right, and because we zone with things like zone valves, okay, that high flow, low head, flat curve circulator works with zone valves in particular, but even with zone pumping beautifully. So that's why an American style curve tends to be flat. It fits the types of systems we have traditionally installed here in the US. Now that's changing, right? Because we got a little bit of everything now, right? It's changing, but that's kind of the reason a traditional American style circulator will have a flatter curve pump like the B&G 100, the Taco 110, the Taco 007, high flow, relatively speaking, low head, flat curve circulators, compared to a European style circulator that'll have a steeper curve, lower flow, higher head for those types of applications. So that's why we have the difference. Okay, that's why we have the difference. Now, all that being said, let's talk about system curves. The pump curve is the pump curve. It's the performance curve of the circulator we select. It's important to understand that once we put a circulator on a job, that circulator is going to determine what's going on. Okay, the system must work somewhere along that pump performance curve. Okay, energy in equals energy out. The boiler makes the heat emitters deliver the heat, but it's the circulator that decides how that water's moving from one to the other and back again. And it's going to work on its pump curve. Where on that pump curve? Well, now we have to understand something called a system curve. And before I jump into this, I just want to double check any questions out there. How would you calculate pressure drop in a cast iron radiator? That's a good question, Carmen. There's not much. There's not much. And honestly, here's the way I've always done it. I just figure I got a cast iron radiator. Let's say I'm piping it up with 3/4 inch copper, just for an example. I would just take that length, 3/4 inch and call it 3/4 inch copper, and I know I'm good because there's just so little pressure loss through a cast iron radiator. I would figure it as 3/4 inch copper. If anybody else has a different way of doing it, please chime in. But that's kind of that's the way I've always done it, and I'm safe that way. Okay, let me know if that helps, Carmine. Alrighty, system curves. Let's take a look at system curves. As flow goes up, if you follow this curve, okay, as flow goes up, the head loss is going to go up exponentially. It's not a straight line, you'll see. It kind of shoots up like a rocket ship. All right, and there's a math formula for it, and I'm sorry, I'm going to burden you with it, okay? The importance of the system curve is, let's say I'm doing my math and I come up with 3 gallons a minute, add 1, 2, 3, 4, 5, 6 feet ahead. So this is where I want my system to actually operate. But as you can see, it can't because it has to work up here. All right, so if let me do this. Let's say this was 3 gallons a minute at 6 feet ahead, just so it'll make a little bit more sense. If I follow the system curve to where it intersects the pump curve, this is going to be where I'm actually operating. Whatever that flow rate might be, all right, at whatever head pressure differential it might be, based upon that intersection point. The system must work where the system curve intersects the pump curve, all right? It has to. Now, once you know your requirements, that 3 gallons a minute at 6 feet ahead, we can plot the system curve using a math formula. All right, so I already know 3 gallons a minute at 6 feet ahead. I know one point on that curve. I also know another point on that curve, 0 at 0, right? Because no flow, no head. So I know that part. Now, mathematically, I can figure out the other points on the plot, okay? And there's a math formula, and I'm going to apologize for it in advance. Here it is, okay? Head 1 divided by head 2 equals flow 1 divided by flow 2 squared, all right? Now, what's going to happen here is you know 3 of the 4, all right? You know flow 1 and head 1, okay? That was 3 at 6, right? We know those two. We know 3 gallons a minute. We know 6 feet ahead. What we'll do is we'll plug in another flow rate. So let's say 6 gallons a minute. We'll plug in 6 gallons a minute, and if we follow the math, that'll determine what head 2 is. And this is just algebra, and we're going to solve for x. Okay, we're going to solve for x. The thing is, I want to go from 3 gallons a minute at 6 feet ahead. If I do 6 gallons a minute, it's not 12 feet ahead. It's something much greater. All right, so let's do the math. All right, 3 gallons a minute at 6 feet ahead. We put in all of our information. So head 1 is 6 divided by x equals 3 gallons a minute divided by 6 gallons a minute, and that's what we're trying to solve for, squared. So 6 divided by x equals, if I do 3 divided by 6, that's 0.5. Okay, so 6 divided by x equals 0.5 squared. We continue our math. So 6 divided by x equals 0.25. And again, simple algebra, whatever you do to one side, you got to do to the other. We want to solve for x. So what we're going to do is multiply both sides by x, all right, to start the isolation process. So now we have 6 equals 0.25 times x. Now to solve for x, we're going to divide both sides by 0.25, and you're going to see that x, the new head, at 6 gallons a minute is going to be 24 feet of head. So we went 3 at 6, then we jumped up to 6 at 24, all right, 6 at 24. So that's how we figure out head loss. And we can plug in different flow rates here. We can do 4, we can do 5, whatever we want. We can do all those different numbers. That's how we get our points on the plot, to plot out our system curve. You remember doing charts and graphs? I think it was in 5th or 6th grade math. Anybody remember doing that back in 5th or 6th grade math? And you're thinking to yourself, this is stupid. When am I ever going to use this stuff in the real world? I'm never going to do charts and graphs in the real world. Today's the day, boys and girls. Today's the day. So all that stuff we learned back in 5th and 6th grade math that we thought was useless actually does come back to haunt us. All right. There is an easier way. There is an easier way, and that means using the Bell and Gossett system sizer wheel. Bell and Gossett system sizer wheel, developed by Gil Carlson back in the 50s, one of the single greatest inventions in hydronics history. I have a copy of the original sitting about 6 feet to my left that was hand drawn by Gil Carlson. But it's a scale, a wheel that allows you to do a lot of different math. You can do your universal hydronics formula, GPM equals BQH divided by delta T times 500. You can use it to figure out head loss. You can use it to figure out different flow rates. And using scale number 5, we can plot out a system curve. We don't have to do all that math. The math is done for you right here, okay? And right here on the lower side. So let's take a look. The way you would do this, all right, is you line up in the window here, you line up your flow, all right, and your head. You line up flow and head right there. So 3 gallons a minute, 6 feet ahead. Once I line that up, now I can go both to the right and to the left and find the head loss at different flow rates. So if I were to go, let's go to the left here. So 3 gallons a minute, 6 feet ahead. 2 gallons a minute, 2.8 feet ahead. All right. If I want to go all the way here to 1 gallon a minute, 0.7 feet ahead. Let's go the other direction. 4 gallons a minute, looks like 11 feet ahead. 5 gallons a minute, 17 feet ahead. 6 gallons a minute, 24 feet ahead, which we mathematically showed you, and so on and so on. That's an easy way to figure out the different points on your system curve plot. And once you have those points on the plot, once you have those points, you just put them on a piece of graph paper or put them on your pump curve chart. And once you have them all, then you connect the dots, and there's your system curve. All right, there's your system curve. Why is this important? Well, on a piece of graph paper, it isn't. But this is going to exist no matter what circulator you put on that. That system curve is not going to change regardless of what circulator you're going to put on the system. What's going to change is where that system curve intersects the pump curve of the different circulators. So let's take a look at that. This is the Taco 0015 3-speed residential circulator and the 0010 3-speed residential circulator. You see the 0010 is a flat curve circulator, high flow, low head flat curve. The 0015 is like many others that are common in the industry, the Grundfos 1558, the B&G NRF 22, etc. All very similar in terms of performance. All right, and as you can see, we plotted out our system curve. We connect the dots, and we see where we intersect. And you can see this is where we want to be. If we're looking at that, which circulator and what speed would you choose? What would be your best selection here? What circulator would you choose and what speed would you set it at? Type it on in. Let's see what you got. I'm waiting. Let's see what you got. Should be pretty obvious. Which one would you put on here? We got the 0010 at low speed. Okay, 0010 at low speed. Not a bad choice at all. Not a bad choice at all. We're a little above that line, but that's okay. The worst that could happen here is under design conditions. If everything is dead on accurate and there was no fudge factor in the heat load or anything else, the worst thing that would happen if we were a little above that line would be under design conditions, our delta T might be a little wider than 20. Oh, the horror. Okay, that's not a bad thing. All right. More likely, simply because of the price difference between these two, all right, the price difference and availability between the two, you're going to find that you'll probably go with the 0015. That's going to be a likely scenario. All right. Now, that point, I'd be operating right there at about 7 feet ahead and a few extra gallons per minute. Let's see where we're at here for gallons per minute. Yeah, I might be at a little over 3 gallons a minute, just a shade over 3 gallons a minute. I might have a slightly smaller delta T than 20 under design conditions, but we can live with that. We can live with that. So not a bad choice in either direction. A really good question from Steve Metlak. Does the number of zone valves in a system affect your choice of flat versus steep curves? No, it doesn't. If I have zone valves, I'm going to virtually always go with a flat curve pump. Flat curve circulators and zone valves go together like cake and ice cream, okay? Steep curve pumps and zone valves go together like tuna fish and ice cream, meaning not at all. And here's why. Really good question, Steve. That's a really good question. So let's say this is a zone valve system, and this is all my zones are all zones calling. And I'm gonna make up a zone valve system. With a zone valve system, you're gonna have a bunch of system curves. You're going to have one system curve for every possible combination of zones that are calling at any given point in time. All right. Just the way it is. If I got a 3-zone zone valve system, I've got 7 different system curves for 7 combinations that could be calling. Let's count them out. I got zone 1 by itself, zone 2 by itself, zone 3 by itself, zone 1 and 2, zones 1 and 3, zones 2 and 3, and zones 1, 2, and 3, right? That's 7 different system curves. What happens is, as zone valves close, let's just for giggles and grins say I'm using the 0015 at high speed, all right? So I'm intersecting here, or here, or here, or here, or here. Now, I'm going to deliver BTUs, man. There's no way this house is not going to heat. I'm delivering BTUs. But what happens is when I get up into this range, okay, what can happen is when zone valves close, they can bang, all right? When they're banging against that, when they're closing against that kind of a pressure differential, you'll get what sounds like a water hammer noise. It's not a problem with the zone valve. It's not a problem with the circulator. It's a problem with the combination of zone valve and circulator. So whenever you use a steep curve circulator in a zone valve application, you've got to be cognizant of you might be causing banging zone valves. Zone valves that were banging when, hey, you know, the old pump didn't do that. The old pump was a Takeo 007, which was a flat curve pump. We didn't have that problem. Okay, and a 007 is going to be kind of like the medium speed on a 0010 3-speed circulator. All right, so that's how you make. It's not the number of zones. To me, it's if I'm doing zone valves, I'm not going to bother with a steep curve pump. What's the point? There's no reason to. I'm going to be creating a problem where I don't need to. Now, a lot of folks will say, well, you just put in a pressure differential bypass valve. Gang, that's a band-aid for a self-inflicted wound. What a pressure differential bypass valve does in that example is it simply turns a steep curve pump into a flat curve pump. Well, if it just turns a steep curve pump into a flat curve pump, why on earth would we be using a steep curve pump in the first place? It's a self-inflicted wound. Basically, what you're saying is, I'm going to create a problem right here. And just a few feet later, I'm going to spend more of my customers' money to solve the problem that I just intentionally created. Doesn't make any sense. Flat curve pumps and zone valves, cake and ice cream. Let me know if that makes sense, because that's a really good question, Steve. I appreciate you asking. All right. Is this any different if you use modulating zone valves? No, because if they're going to be closed, at some point they're going to close anyway, right? At some point they're going to close anyway. So that's just the way it is. If you get a flat curve pump, do you need to upsize the pipe and flow? No, flow is flow, all right? Whether it's a steep curve pump or a flat curve pump, if I need 3 gallons a minute at 6 feet ahead, I need 3 gallons a minute at 6 feet ahead. So I don't need to, flat curve, I can't understand why that would necessarily cause you to upsize the pipe or the flow. Let me, Nicholas, if I'm understanding your question right, if you could restate that or let me understand. I want to help. I want to make sure I understand what you're asking. All righty. Whew. How we doing? We're cruising. All right. Let's talk about CV now. CV, there's a lot of different names for it. It's coefficient of velocity. It's constant velocity. Really what CV is, it's a way of measuring the pressure loss through a piping component, like a valve, like a zone valve or a mixing valve, that sort of thing. It's a way to express that, all right, in a number so we understand what it means. And again, the actual pressure loss through a valve is going to vary based on the flow rate through it, all right? So let's take a look. It's, again, flow coefficient is a good term for this. It's a relative measure of efficiency through that valve to allow flow. And it's what it is. It's the flow rate of 60-degree water across a piping component needed to create 1 psi of pressure drop. So the CV rating of a valve, okay, CV rating of a valve is the flow needed across that valve to create 1 psi of pressure drop. So, for example, if I had a valve that had a CV rating of 5, that means at 5 gallons per minute, that valve will impart 1 psi worth of pressure drop. All right. If the valve has a CV rating of 5, it means that across that valve, 5 gallons per minute of flow will create 1 psi of pressure drop. And 1 psi of pressure drop, as we know from earlier, is equal to 2.31 feet of head loss. Okay, 2.31 feet of head loss. If I had another valve, a completely separate valve, that had a CV rating of 10, that means across that valve requires 10 gallons a minute in order to create 1 psi of pressure drop. Okay, the higher the CV, the lower the pressure drop across a piping component. All right, that's an important thing to remember. The higher the CV rating, the lower the pressure drop across that valve or whatever it might happen to be. All right, now here's the thing. Just like we did with system curves, okay, the pressure drop across that valve is not linear. So if I have a CV of 5 gallons a minute gives me 1 psi of pressure drop. 10 gallons a minute through that exact same valve does not give me 2 psi of pressure drop. It gives me a lot more. It's exponential, like we talked about earlier. So let's take a look. Here's the math formula. The known flow rate you're trying to pump through a valve divided by the CV of that valve squared times 2.31 will give you the pressure loss through that valve in feet of head. All right, so flow divided by CV squared will give you the pressure loss in PSI. Multiply that by 2.31, you get your pressure loss in feet of head. All right, let's do an example here. Okay, let's do an example and show you why we care. Why do we care? Well, this is why we care. Okay, these guys right here, mixing valves, things like that, zone valves to a degree. All right, the Taco zone sentry zone valve, for example, the 3/4 inch zone sentry zone valve has a CV of 10.3. Okay, 10.3. What does that mean? It means through that 3/4 inch valve, 10 gallons a minute of flow will equal 1 psi of pressure drop or 2.31 feet of head. Now, typically, if we were doing a 3/4 inch zone of fin tube baseboard or 3/4 inch zone of anything, all right, our maximum flow rate's going to probably be about 4. What does that tell us? That tells us the pressure loss through that particular the zone sentry zone valve is very, very minimal. All right, that can be taken into account with that 1.5. It's that low. You look at something like the 571, the heat motor zone valve. That's a little bit different. The CV through that is actually the equivalent. It makes that zone valve the equivalent of 20 feet of pipe. All right, so it depends on what you're using. Okay, check the ratings of whatever zone valve you use, and that'll tell you where to go. All right, let's take a look. Let's do an example. I've got a radiant system and I'm going to use a 3-way thermostatic mixing valve, and I want to find the pressure loss through that mixing valve. So my radiant manifold requires 6 gallons per minute, and the pressure loss through my worst case loop on that manifold is 5.5 feet ahead. So just through this manifold here, 6 gallons a minute, 5 feet ahead. I have to also take into account my supply and return piping. All right, copper pipe supply and return. Let's math that out. And let's say that's an additional 3.5 feet ahead. So I've got 5.5 feet ahead through the PEX, 3.5 feet ahead through the copper supply and return piping. That's 9 feet ahead. So I could use a circulator who does 6 gallons a minute and 9 feet ahead. That sounds great, right? But I got to take into account the pressure loss through the mixing valve, through that thermostatic non-electric mixing valve. All right, and what would that be? Well, here's again, these are the Taco models. All right, so let's take a look at the 3/4 inch. All right, we'll take a look at the 3/4 inch. The thing about non-electric tempering valves is they have very low CVs, relatively speaking, which means they have high pressure drops, relatively speaking. So let's take a look and see what we have here. All right. So 6 gallons per minute, at 6 gallons per minute, I'm going to look at my 1-inch valve, and the 1-inch valve has a CV of 3.8. All right. The chart tells us the PSI as well as the head loss. So we're looking at another 5.76 feet ahead. Let's math that out just so we know. 6 gallons a minute, that's the flow, divided by the CV rating of 3.8. Squared times 2.31, that'll equal your 5.76 feet of head. That's where that number comes from. So I have to add that to my 9 feet of head. Okay, we add them up. 5.5 feet of PEX head, 3.5 feet of supply and return head, and 5.8, let's call it, feet of a valve head. That gives us a total of 14.8, we're going to call it 15 feet ahead. So now I need a circulator that'll do 6 gallons per minute at 14 feet ahead. So 15 feet ahead. That's what I'm looking for when I pick a circulator for this radiant job. So let's see what we come up with. Well, here we go. 6 gallons a minute at 15 feet ahead. That's just on the outside of the 0015 at high speed. You know what? Again, that'll work okay, because one of the things we always understand about heat loss is when we do a heat load and we came up with the 30,000 BTUs we needed for that 6 gallons a minute in the radiant system at a 10-degree delta T, we understand that, you know what, there's fudge built in there. All right, we had to do a heat load calculation on a piece of paper, looking at a blueprint and interpolate what the actual constructed house would lose. The biggest piece of fudge we have there is heat loss due to infiltration. Okay, that's just not a stab in the dark, but by definition, that's a very broad view. The only way to really know what the infiltration is after the house is complete, you do a blower door test, then you got an accurate depiction of that. But we understand that, you know what, that's 6 gallons a minute, that's very, very generous. So I would be perfectly happy here putting that, putting the 0015 on high for that application. That'll be fine. That'll be fine. All right. If I were to go variable speed, okay, the 0015E3 ECM variable speed, I would still choose high, because again, I'm a little bit outside the line, but you know what? Understanding that my heat loss is probably lower than that, what the 6 gallons per minute reflects, I'm going to be fine. Now, in this case, at high speed, all right, I got a full speed, fixed speed circulator. This particular circulator at high speed is not variable speed. It's full speed, fixed speed at 44 watts. All right. Medium and low, now those are going to be the variable speed operating points for this circulator. And they're constant pressure delta P. So we'll be working somewhere along this line or somewhere along this line if I was able to choose those. Let's say I'd like to choose that. How would I do that? How could I redesign this system to get my head loss lower? What would be the easiest thing to do? Let's see what you think. What if you wanted to get the head loss lower? How would you do that? Okay. How would you do that? Larger mixing valves, good, Lauren. Yep, larger mixing valves, larger pipe. You could do that too, but it's already. Let's take a look at it's already been installed. You know, or do I want to go with 5/8 inch PEX in a slab instead of 1/2 inch PEX? That's going to have cost ramifications, okay, on a larger scale. So you've got to make that decision. It'll certainly do that. Higher CV. Let's look at a higher CV mixing valve. It might be the easiest thing to do. A higher CV mixing valve. And now we're going to look at the Taco I valve. It's a motorized mixing valve. Okay, in this case, it's a 3-way valve, a motorized 3-way mixing valve that has a slightly higher CV. But on top of that, in this little green box here, is a fully functional outdoor reset control. Whereas a tempering valve, that fixed temperature tempering valve is by definition fixed temperature, meaning whatever water temperature you set it up for, bam, that's what it's going to give you. The Taco I valve will give you outdoor reset. You have an outdoor sensor for this thing, and it will change the water temperature based on how cold it is outside. So you get a twofer here. You get a higher CV rating as well as outdoor reset. It's kind of a nice solution. So again, it's a motorized 3 or a 4-way. We're going to look at the 3 ways here, and you see the different CVs for the different models. Okay. So in this example, in this example, 6 gallons a minute, let's use the 1-inch union that has a CV of 4.5 compared to 3.8. Doesn't sound like a lot, but looky-loo, we've dropped that extra head loss down to just a shade over 4 feet of head instead of 5 3/4. Now we're just over 13 feet ahead. Now, just over 13 feet ahead, you can see we're well within the guidelines here. All right, we're well within the 0015. We're still good. We're going to be outside of that variable speed portion right here. So is there another solution? Well, we looked at the 3-way valve. Again, we want to get that head down to about here. All right, we want to get it down to about there, down to around 10 feet ahead. Let's look at the 4-way valve. The people I say, what's the difference between a 3-way valve and a 4-way valve? It's one way, okay? 3-way valve has 3 holes, 4-way valve has 4 holes. Other than that, they do the same thing. But realistically, what a 4-way valve does here is that it lowers the pressure loss, okay? It's designed for higher flow rate applications. It lowers the pressure loss. So it has a higher CV and a lower pressure loss. So let's look at 6 gallons a minute. Hey, my line size, my pipe size to and from that manifold is 1 inch, right? So I could use the 1 inch valve here with a CV of 9.3, and look at that, it's a foot ahead. Man, we're fine. Let me suggest this to you. You might be better served with the 3/4 inch valve. And here's why. The head is 1.69 feet. Let's work with that one first. 1.69 feet of additional head. So now my total head is just over 10 feet. Okay. Now with my 3-speed pump, I'm firmly in the medium category here. But now I'm going to be okay with medium here. And if I have manifold actuators on that manifold that act like zone valves, now I'm going to get variable speed. Okay, now I'm going to be able to use this pump to its maximum capability and have it speed up and slow down as those zones open and close, which is really cool. But wait a minute, I got a 1 inch pipe and I'm going to a 3/4 inch valve. That makes no sense. Sure it does. Let's take a look back here. Think about a 4-way valve, especially this. This is a reactive valve, meaning what it's going to do is it's trying to give you a water temperature, okay? It's trying to match the water temperature it delivers to the outdoor temperature. So as it gets colder out, the water temperature goes higher. As it gets warmer out, the water temperature goes lower. It's your outdoor reset. It's a motorized mixing valve. So that motor moves the flapper inside that valve to create the mix at a fixed speed, okay? It's doing this, right? What it's doing is it's hunting for a water temperature. The bigger the valve, the wider the hunt, all right? The smaller the valve, the narrower the hunt. This is what we call valve authority. If we use that smaller valve, think about how it's going to react to changes, okay? Let's say there's no call for heat, and then all of a sudden, okay, we get a call for heat. The valve says, based on the outdoor temperature, I need 120-degree water going through the radiant system. Okay, that's what the outdoor sensor says. The sensor on the radiant supply pipe says, hey, the water temperature is 90 degrees. Okay, my pumps are running. What is this valve going to do? It's going to start to open to allow more hot water in to get the temperature up to 120. Really big valve, going to have really big movements. So we're going to allow a lot of hot water in a hurry. So maybe that water temperature bolts up to 140 real quick, and the valve goes, oh, that's too hot. I'm going to start to squeeze it off. Now I go down to 95. Whoa, got to start opening up again. And you're going to be bopping back and forth. You'll eventually get to the water temperature you want. With a smaller valve, that hunt is narrowed considerably. Right? Best analogy I can think of is basketball, right? Who brings the ball up court? It's not the 7'7" Yao Ming guy, okay? Who, he's bouncing the ball, it's going, it's got a long travel between his hand and the floor, and a small little guy can come and steal the ball from him. Now, the guy that brings the ball up is the point guard, okay? And he's moving the ball between his legs, and there's not a lot of distance between his hand and the floor. He has more control. This is the same thing, only different. So when you're thinking about a mixing valve, especially a 4-way mixing valve, the smallest you can use and still keep the head loss, the overall system head loss, where it needs to be for the circulator want to use is going to be to your advantage. You'll have better water temperature control when you use a smaller valve. All righty, this was fun, huh? All right, here's one more thing. Hey, you know what? We talked about variable speed pumps. What if we use the VT2218? That is a circulator that varies its speed based on maintaining a delta T within the system. So this is a radiant system, and let's say we designed it to a 10-degree delta T, or a standard residential system that we designed to a 20-degree delta T. With the VT2218, we put sensors on the supply and the return piping to whatever it is we're pumping, all right? And that circulator will speed up and slow down to maintain the designed for system delta T, all right? Great way to vary the speed of a circulator, and according to the Department of Energy, it's the most efficient way to vary the speed of a circulator as well. The thing is, it's got to be within this wedge, okay? This is, B is max, okay? You can't go faster than max, right? And A is min. You can't go slower than min. So in this system curve, these points down here, okay, I'm never going to work here or here. I'm going to be working on this minimum speed. So at that point, it's a fixed speed circulator that consumes about 9 watts. That's not horrible. But between here and here, as zones open and close, the circulator will speed up and slow down. It'll also speed up and slow down when used as a zone pump based on the load. The load's going to constantly be changing with the outdoor temperature, right? So this thing's going to speed up and slow down to maintain a delta T when used as a zone pump or when used as a zone valve pump. So it'll work very well in both applications. All righty, Hot Wheels friends, how was this? How was this? Did you enjoy this? Let's go back and check out some questions, okay? What kind of questions are you looking for? Or what kind of questions do you have? I'm going back over a few of these here. The valve needs authority to control properly. I think hopefully I explained that well, Bill. Again, for the purposes of today's discussion, we want to make sure we have a narrow hunt for temperature. All right, we want to make sure we have a narrow hunt for temperature to better control the temperature within the system. If I use a really big valve with a really low pressure drop, and let's say this is, whoops, excuse me, let's go back one. And let's say this is the temperature line I want, I could be going at it like this before I get to that water temperature, okay? If I have a valve with a narrower hunt, okay, I might be like this and get there a lot quicker. That might be the best way to explain it. I just get to the temperature I want quicker and more consistently. So I'm not, too hot, too cold, too hot, too cold. I minimize that, get you the right temperature to the system as quickly as I can. Let me know if that explanation works for you. I've always used line size valves for 2 position and start with 1 size less for modulating. That's a good rule to follow, Steve. Yeah, absolutely. I think that's a good rule to follow. Again, always look at the numbers too. Always look at the numbers, because you go down a size, you might have depending upon who makes the valve, it might be, it might really be a low CV high pressure drop valve. So just check the specs, but I think what you're looking at there, Steve, is a good basic approach. Okay. Is valve authority important for other types of control valves, or does it depend on the valve type? For example, would it be important on a throttling valve? Any kind of valve that is electronically, where the position of that valve is electronically moved. Okay, that's kind of what we're looking for. Again, a motorized mixing valve is the one that I pay the most attention to. So I think that's really where you want to pay attention there. If you're looking at a throttling valve like a globe valve or something like that, not so much valve authority, because you're setting it and you're leaving it. All right, so it's not really moving, if I understand your question correctly, David. Let me know if I have, because that's a good question. All right, cool. Did I miss anybody else's questions up here? Let me go back and see if there's any I missed. Boom, boom, boom. So if you're not going to have 10 gallons per minute in system, then there's no pressure drop. That's Deb. No, there's still going to be pressure drop. It's just going to be, I think you're referring to the zone Sentry zone valve. It's simply going to be a lot lower. Okay, and we can figure it out. So we know the flow, right? So we go back to that formula. 4 gallons a minute divided by the CV of 10.3. Just for giggles and grins, let's call it 10 squared. All right, times 2.31, and that'll tell you the head loss at 4 gallons a minute through the zone Sentry zone valve. So it's going to be 0.4 squared. 0.4 times 0.4 is 0.16. 0.16 squared is whatever it is, times 2.31. It's going to be maybe a foot ahead, maybe if that. Okay. Is that good? Actually, it's going to be less. It's going to be far less than that. So, but that would be the formula, Deb, to figure that part out. All righty, very good. What else do we have? Oh yeah, Alan, you had the same setup. I wish I still had it. I love me some Hot Wheels, man. A rainy Saturday afternoon, I'd spend all day in the living room with two drag race strips, and just doing a head-to-head competition with all of my Hot Wheels. And I had a silly amount. So yeah, that was fun. Those were good days. My nephew wound up getting them, and then I don't know what happened to them. I don't know if he still has them or not. So that's the way it goes. Alrighty, folks. So happy that you were with us today. Really enjoyed this. I hope you guys enjoyed it as well. Again, I'll throw a last minute call out there for questions, and if not, we can say thank you to. I would say thank you to you, and I really appreciate everybody being here. It was great fun. I love doing these things, and especially on a it's a rainy Tuesday. I don't have any Hot Wheels to play with, so I might as well do this, right? Okay, folks. Hey, thank you so much for the gift of your time today. We really appreciate it. You will be getting tomorrow at noon. Noon Eastern. You will be getting an email from us that will have a link to download your certificate of attendance, as well as a link to view this recording, and you can view it as many times as you want. That's easy enough to do. So we do appreciate the gift of your time. Hope you all have a wonderful rest of the week, and a happy Easter to you as well, Dan, and to everybody who celebrates that as well. So thankful, and we will see you next time. Take care, everybody.